Have you ever wondered what powers your smartphone and computers? It's all start with semiconductors. And today we will learn about chapter 1.7, which is on intrinsic semiconductors and explain how they work at the atomic level. And it is very important to understand the concept behind intrinsic semiconductor because they are very essential for the modern electronics. All the electronic devices use a semiconductor, for example, LED solar panels. So in chapter 1.7 we have intrinsic semiconductor. And the first question is, what is a semiconductor? A semiconductor is a material that can sometimes carry electricity and sometimes block it. So they sometimes carry the electricity and sometimes they block the electricity. And depending on how it is treated and the condition around it, the conductivity can be controlled by impurities and temperature and voltage. The conductivity of a semiconductor is between conductors and insulator. So the conductivity of a conductor is, for example, if it's copper, for copper it will be 5.96 into 10 to the power 7. And if it's an insulator, for example, we can take glass, it will be less than 10 to the power minus 11. So there are many kind of semiconductor. There is silicon, then germanium. And if we look at silicon, we can see that the conductivity is 1.56 into 10 to the power minus 3. And if it's germanium, it's 4.6 into 10 to the power minus 11. And we also have single element semiconductor. These two are single element semiconductor. So for single element semiconductor, we can see these two examples. Silicon is the 14th number in the periodic table and germanium is 32. But if we look at the compound semiconductor, we can see that there are many examples, but we can use the most used one, which is gallium arsenide. So gallium is 31 in the periodic table and arsenide is 32. If we use these two together, we have a compound semiconductor. And the interesting thing is more than 90% of the electronics devices are made out of silicon. And this is why silicon is very dominant in the industry, and it's also the reason behind its dominance is that it's very available, and it's also thermally stable. The another thing is silicon oxide is a very strong dielectric insulator. So we can use it in different kind of fields. And so first we will see how a silicon looks like when we go to the atomic level. So silicon has 14 electrons, and 14 protons. I'm not sure about the 14 protons about thing, because I think it should have 14. But if we look at the electrons around the shell of a silicon, you will see that in the first shell we have 2 electrons. The second one, in the second one we have 8 electrons. So we have 4, 5, 6, 7, 8, and in the last one we have 4 electrons. 1, 2, 3, 4. So these 4 are valence electron, and these 4 valence electrons, they share silicon can share these electrons with other silicons, and what they do is they make crystal. So if this is a silicon atom, it makes covalent bond with other 4 silicon, so it becomes like this. And as this is a 2D surface, I'm not able to show you how the crystal exactly looks like, but you can just look into it in the internet, and it's very it exactly looks like a crystal. And these are covalent bond. So what we can see here is that this silicon is electrically neutral. We can actually do an example of the structure of the crystal structure. So if we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 silicon, we can make a crystal out of it. So here we have if it's like +4, I think. What we can do is we can look into the crystal structure of the silicon. So let me fully draw the thing. In real life it's very different, but just to understand how the crystal looks like and how silicon shares the electrons and how the whole electrons work together, we will just use this example. So we know that it has 4 electrons in its valence shell. So this can be the electrons, and what we can do here is you can use this raw silicon to make silicon wafer, and then we can use the silicon wafer to make the ICs, and use the ICs to make the chips. And as we are talking about intrinsic semiconductor, it means that it only includes silicons, and the characteristic of the intrinsic semiconductor at 0 Kelvin is that it has no electron to conduct, and that's why it acts like an insulator. And at room temperature, the free electron are able to conduct electric current because there is an electric field that is applied to it. And and we have to see how it actually works. So for example, we have a electron here, and what we can do is, what if this electron moves from here to here? So we have an electron here, and then here we have a hole, and the hole is a positive charge and the electron is a negative charge. And then what will happen is this electron will move to this hole to make it neutral, and we will have another hole here. And as there is a movement of electron, there will be a movement of holes. And this electron hole pair, like the movement of electron is also causing the movement of the holes, and that's why also the holes are moving, and that's why also the holes are these are like positive pole, and these are charge carriers. And because of the electron hole pairs, the conductivity of silicon is, as we already saw it earlier, it's 1.56 into 10 to the power minus 3. And the important things for this is to understand the thermal generation of electron hole pairs. So we'll just quickly try to understand it. Of electron hole pairs. So what is the main topic of this concept is the number of electrons are equal to number of holes. That's why the concentration of this, like both of the concentration are equal. So what we can say from this is that the recombination electrons fills the hole. It fills holes, and the rate is the proportional to the concentration, and the concentration is proportional to the thermal generation. That's why the recombination rate is equal to the thermal generation rate. And for intrinsic semiconductor, N is, we need this to do the maths of semiconductor. So N is the concentration of free electron, and P is the concentration of holes. So for intrinsic semiconductor, as we already know that the concentration is equal, we can say that N is equal to P, and this is equal to Ni, and Ni is the number of free electrons and holes in a unit. In volume, and this is for intrinsic semiconductor. There are other kinds of semiconductor which is discussed in chapter 1.8, which is extrinsic semiconductor, where we have semiconductor at like atomic atoms, and then we use doping to make it extrinsic semiconductor. And for the Ni, which is the number of free electron and the holes in a unit volume for intrinsic semiconductor, we can say that Ni is equal to Bt to the power 3 over 2 and e to the power minus Eg over 2 kT. And here B is a material dependent parameter. And we also know the value of B. It's 7.3 into 10 to the power 15 centimeter cube Kelvin 3 over 2. This is only for silicon. And then T is the temperature in Kelvin, and Eg is the band gap energy. And this is 1.12 electrovolt. And K is the Boltzmann constant. This is very famous constant, and we also know the value of this. It's 8.62 into 10 to the power minus 5 electrovolt per Kelvin. So from here we can also see that Ni is Ni square equal to Pn, and we know that P is the concentration of the holes and N is the concentration of free electrons. So from here we can easily find out the number of free electrons and the holes in a unit volume for the intrinsic semiconductor. And the most important topic is the question is why the thermal generation is not enough for a meaningful current conduction. Because there are not enough number of carriers. Carriers are the free electrons, and also as we saw that holes can be charge carrier, so holes. So that's why we introduce a new thing, which is doping. And doping is the introduction of impurities in pure semiconductor, pure intrinsic semiconductor, for increasing the carrier concentration. And it also is precisely controlled so that we know how much material we are introducing in the semiconductor. So after this we have chapter 1.8, where we talk about doped semiconductor, but it also is extrinsic semiconductor. And there are two types of doped semiconductor. One is N-type, another one is P-type. And N-type is type of semiconductor that are doped with elements that has a valence of 5. Means it has 5 electrons in the outer shell. And we use this to increase the concentration of free electron. There is an example of this in the periodic table. It's called phosphorus. And this is known as a donor because they donate free electron. And for doing the math, we use NN. This is N-type. This is the concentration of free electron. And we use Pn, which is the concentration of holes. So before doping, we know that Ni is equal to Ni was the concentration of it was, I think, the number of free electrons and holes in a unit volume for intrinsic semiconductor. So Ni will be equal to, before doping, N-type semiconductor free electron an n-type semiconductor hole. This is before doping. And after doping, the donor concentration, which is ND, we use the subscript D as for donor. ND will be very, very larger than NI. NI will be very, very less than ND. And the concentration of free electron, which is NN, will be approximately equal to ND. And from here we know that Ni is equal to Pn. This is the concentration of hole, this is the concentration of free electron. So Ni square is equal to Pn and Nn. Pn is the concentration of free holes of the n-type semiconductor, and Nn is the concentration of free electron in the n-type semiconductor. So we can rewrite this as Pn Nd. Nd was the concentration of the donor, concentration of the donor after doping, and from here we can figure out what is the concentration of concentration of the holes of the n-type semiconductor. It will be approximately Ni square over Nd, and we know that Ni was number of free electron and holes in a unit volume for the intrinsic semiconductor, and Nd was the after doping the donor concentration. So this was for n-type semiconductor. Then we have p-type semiconductor. And in this case, we have the semiconductor that are doped with elements that has valence of 3. So to increase the concentration of the hole, we use this. And we have an example in the periodic table. We can use boron, because boron accepts an electron with the hole. So that's why it's called an acceptor. And we can see the diagram. So if we have 3 electrons in the valence shell, it accepts electron. So we can use the previous diagram for this case to understand how it works. So for this case, it will not have 4 electron. Instead, it will have like 3 electron on the outer shell. So I'll just draw the basic, just to understand the basic thing. So we have a hole here because it has 3 electron. This is a hole, and then this is the free electron is the concentration Np, and the whole concentration is Pp for p-type semiconductor. And before doping, exactly similar to the n-type semiconductor, we have the concentration of the free electron is equal to concentration of the holes is equal to the concentration of the, I always forget what is Ni is. It's Ni is the number of free electrons and holes in a unit volume. Free electrons and holes in a unit volume. Okay, so Ni and the holes in concentration of the free electron and the concentration of the holes are exactly equal to the number of free electron and holes in a unit volume for intrinsic semiconductor. And after doping, the acceptor concentration is Na. So for the n-type semiconductor, we had Nd, which is the donor concentration, and Na is the acceptor concentration. exactly like in N-type semiconductor, for P-type semiconductor, the acceptor concentration is very, very high than the concentration of the free electron and holes in the unit volume of for the intrinsic semiconductor. And then from here we can say that the concentration of the holes for the P-type semiconductor is approximately equal to the acceptor concentration. I know it's a lot of word, but this is like a fundamental idea to understand the semiconductor, and we need to understand this to understand how electronics devices work. That's exactly like the previous N-type semiconductor, we can say Ni square equal to Pn, and then Pn, this is for N-type semiconductor, and then Ni square equal to the acceptor concentration, and P is the concentration of the electron, the P-type semiconductor. So for majority charge carriers in the N-type semiconductor, we have electrons, and the majority carriers in the P-type semiconductor, we have holes. So electrons are like this and holes are like this. And then we have the concentration of the N-type semiconductor is approximately equal to concentration of the donor electron, and the concentration of the P-type semiconductor, concentration of the holes in the P-type semiconductor is approximately equal to the concentration of acceptor atoms. So the majority carriers, from here we can say that the concentration of holes in the N-type semiconductor is approximately equal to the concentration of the number of electrons on the holes in the unit volume of an intrinsic semiconductor square divided by Nd. Nd is the concentration of the donor electron, and Np, the concentration of electrons in a P-type semiconductor, is approximately equal to Ni square divided by Na. N is the concentration of acceptor atom, and Ni, I'll just double check, it's number of free electrons and holes in a unit volume for an intrinsic semiconductor. And we can use this formula just to figure out the concentration of these holes and electrons, which we will use to understand the semiconductors.